That's the one that I forgot to mention. That as best as I can, I'll try to remember to record everything. Um, and I'll post them on YouTube and put it on the class website as well. So I'll have to do another introduction later. But yeah, majority, if no there's no technological difficulties, then I'll record everything and post it on YouTube. So if you really can't make it to class for whatever reason, then some of the materials are online. I don't suggest missing anything, just because some of the exercises, especially in this the first portion of the class, which is the quantum mechanic one, usually most chemistry classes don't cover it as much. But the UCLA one, the UCLA syllabus does cover a lot more of the quantum mechanics than most colleges that I've taught in. Yeah. This is this is an intro chemistry class, but the prerequisite is essentially high school math and high school chemistry. Okay. Do you know what a mole is? Okay, so so that's going to require some review, but part of the reason I start from quantum mechanics is because nobody knows quantum mechanics, so everybody starts at roughly the same place. So we're going to go and cover some of those as well. That's kind of what I realized after teaching this class several times, that people haven't taken this in like 4, 5, 6, 12 years. So there's things that I just need to brush up. But I believe there should be a class offered by UCI Extension that's one step below this, which is essentially just high school chemistry. If you decided, essentially you come in like this first week and it's like, yeah, I really can't do it, then it's something that you should consider. Or if you want to consider coming to the Saturday one and see whether it's any difference. There's a Saturday Chem 14A class, but usually people survived it. We'll start, essentially we start where everybody's at 0. So yeah, we're going to do balancing chemical reaction again throughout later on. So I think you shouldn't have too much of a problem. As long as you remember your algebra, that's all right. You do need to remember your algebra just because it's a science class. You solve for x. You have multiplications, you solve for one thing. So I think in that regard, it should be okay. I think you're okay. Sorry, I actually forgot to ask your name, and I haven't actually introduced myself. My name is Professor Halim. I'll be your instructor for this time around. My full name is actually Udaya Bagya, but nobody can pronounce it, so Halim it is. That's Paul, Angel, Rachel, and Jonathan. So Paul, what are you taking this class for?
So I'm doing the, I don't know if it's the same place for everybody, but I'm doing the agreement.
Okay.
And so I had a non-science bachelor's. So I'm hoping to go to a science graduate program that I can catch up on all that stuff. The bachelor's was in economics.
Okay. Economics. Okay.
So also a subject that fascinates me, but I want my career to be in the sciences. So
I think economic career would have to give you more money in the long run than the sciences, but
I mean that's not a
okay.
But yeah, so I mean hopefully continue grad school at UCLA, but
Okay.
Or someone else. But yeah, starting out this is my first quarter with the I'm also taking the life science set.
Cool. Then we'll just go around. Angel? All right, Rachel.
I'm a pre-med student. I'm from here, but I graduated from Indiana University from an undergrad. And I went there, but I grade. And I decided to get a certificate as well, so I'm under the
Same thing.
side.
Cool.
I'm really excited. This is another knowledge.
And Jonathan, yeah.
Also pre-medical certificate.
Okay. Oh, cool.
Yeah, it's my first quarter doing it. My bachelor's at CSUN in social science and law, so I haven't taken a science class.
That's all right. All right. So we have 3 pre-meds and 1 dental, which I guess it's more or less about the same track. I think they're pretty identical, more or less. So that's cool. Most of the time, people do really well in the class. You know, I never have people. Okay, there's one person who failed the class, but that's incredibly rare. Essentially, if you don't show up and you just show up during the exams and you thought you know chemistry, that doesn't work that well. So that was what happened last time with that one student. But most of the time, people pass. The pass is the grade breakdown is pretty straightforward. A is at 90%, B is 80, C is 70, D is 60, and below F is, I guess, below 60. So in terms of the breakdown, it's pretty straightforward. So hopefully this goes well, and if this is your first time around, good luck. 4-hour classes. 4-hour class is actually not that long. I mean, it's long, but you'll realize it's not. It goes by pretty quickly, but at least goes pretty quickly for me. But I think you guys should be okay. I'm pretty confident on that. Usually I teach at the CSU at the Channel Island and Camarillo. And usually the students are, right after high schools, and that's when I have to drill to them, you really need to study to finish a class. But most of the UCLA Extension student people that you guys are working, most of you guys are. So, you're taking this class and you're paying a ton of money for it. So you have the incentive to do well. And usually I don't have to remind you to study. But if you do want to study more and ask for extra problems and things like that, let me know. And let me know what particular textbook that you get, although you have 7th editions. And if you all get a 7th edition, it's a bit easier, just because they rearranged the questions a bit between all these chapters. One of the best things to get through is that we're going to try to cover for today, for example, a section 7th edition 1A to 1C, and you'll realize if you go to the chapter 7 in the book and 7A, and after they finish 7A, there's a little bit of snippet of questions. So that's a good way to practice in terms of what topic to start, some additional problems. There is a student solution key and study guide for the textbook, which I recommend for you to get as well if you can. Or if you want to have like one person get it and just like everybody pitch in an extra $6 and just like cut it out and scan it or something in Kinko, then that works out as well. I used to do that for my students, but I got in trouble, so I stopped doing it. But the solution key, I found that the solution key is pretty useful, especially if you just want to pitch in with everybody else. So mostly I've been talking. Do you have any questions for me then? It's a pretty normal class, more or less.
Do you have an area of focus in chemistry? I mean, I'm assuming your PhD is in chemistry.
Oh, yeah.
But
PhD is in chemistry, specifically physical chemistry. Hence, I like the quantum portion a bit more. And if you But specifically, I study semiconductor materials, more on the physics of it rather than on the. It's a chemistry degree, but it's more on the physics side of it, hence physical chemistry. But well, I graduated from UCLA a couple of years ago, I think. But I was a graduate student for like 6 years there. But yeah. So I do know the class, this class pretty well, and I don't know why. So the syllabus that we're going to go is pretty similar to what you've seen on the main campus as well. And I don't know why, but the department seems to just shove all the physical chemistry professors into intro chemistry. Hence, the intro chemistry looks like our class. And it's the first portion is going to be physics, essentially. So I've, in terms of graduated from UCLA, it was a couple of years ago, or maybe last year. Last year? I think it's last year. But I was a graduate student there for about 6 years. And most of the time, I teach at CSU Channel Island, and one semester, 1 quarter, like a night class here once in a while. I do have 14B as well, so if you like me and maybe you want to see me again, then it'll be on Saturday next semester, but I will double check with them, but they are putting the schedule on Saturday. But it's going to be at the downtown LA location instead of here. Huh?
Stay here.
Oh,
I like it here too because it's closer to my house, but
Channel Island, downtown.
yeah.
That's crazy.
Well, I used to commute to UCLA, and you know what? It takes about the same amount of time for me to travel from my house to UCLA than it is to Camarillo. But I'm simply moving like twice the amount of speed if I go to Camarillo. So, but more or less, the travel distance is about the same for me, which is an hour of travels every day. Which is why I listen to a lot of audiobooks. So if you want to have book recommendations, let me know too. Or if you have any book recommendation for me, let me know too. So yeah. Any other question?
Is it only us 4 in the class?
I think it's going to be that. Yeah.
No curve, right?
No curve. Well, there's no curve anyway, so
You get
So the nice thing about having no curve is that sometimes everybody get an A, which makes me happy. But so I think 4 or 5, it's going to be the number that we have. Hopefully they're not going to cancel it, but hopefully it's fine. My smallest class so essentially they somehow they don't like the Woodland Hills is opens on weekdays rather than on weekends. So what happens is that not a lot of people goes into the Woodland Hills one, hence they have like 25 people in downtown LA. My smallest class here is 5 people. So I don't know about less than that. So I think it should be okay. Huh? Sorry?
I said I've seen them cancel some classes.
Yeah. So.
Don't scare me.
So we shall see. We shall see. It was. I think it was 10 people before the schedule changed. So now there's 4. So we'll see. Yeah. Or maybe the rest of them just didn't get the memo and came in. Yes, on Tuesday. So we'll see. But I don't know. I have a feeling it's going to be okay. It's like either this week or next week, and that's that would be messed up. So if you can manage it and just kind of stop by the UCLA downtown LA section on Saturday, just kind of double check and just to see, and whether if it's there's another class at downtown LA, so that's on 9 to 1 p.m. 9 a.m. to 1 p.m. If it's something that you can manage, Angel said she couldn't because she works. If it's something that you could accommodate, then it might be something that you might want to think about. But I don't think it's going to be canceled. There's enough. I think it should be okay. Yeah. Yeah. So, I'm not too worried actually. Usually they cancel it before the first day of class. So yeah.
I don't know if you're going to be going over it, but the thing on the syllabus, the grade scope.
We're going to go into it on closer to the exam. Essentially, because we have a once-a-week class, I usually grade the exam faster. So essentially, what I'm going to do is I'm going to take your exam and scan it, and the grading is going to happen online. So once I'm done, I can just send you an email. You can download a PDF of your work. It's annoying because it's two different learning management systems. We have Canvas and we have the other one, but I found that is the fastest way that I can send you back your work. So we'll get into that closer to the actual exam. All I need from you is just your email address or something like that. Or actually, I don't need it. You can sign up on your own later.
Were the practice problems that you were talking about here, were teaching class assignment?
Yep. You'll see there's a bunch of like blank sections here and there. That's mostly it, right?
Yeah,
We're just going to.
in this packet.
Yeah.
Okay.
So yeah, if you go to the last page, then there's some sample problems and things like that. We'll try to work on it in class, so you don't have anything to do. All right.
Reading.
Right. You have your own reading to do while you're home, but there's no homework. Yeah. Yeah. Anything else? Nope. Yeah.
Sorry, quick question. So you said there's physics involved?
That's fine. That's fine. Which is fine. That you're going to be okay. Oh wait, I'm not going to use the board today, so I'm just going to use this thing. Anyway, so no. Yes, the answer is no. You can put calculus in there, but usually, no, not until you get to upper divisions. That's when you use calculus. So.
Would that be like going into this 14B, or would that be like the next level of class?
Next level of class.
Just want to know when I need to brush up on my
You may want to brush up on your logarithmic rules, because we're going to do acid base, and you have to take pHs, and that's when you need your logarithmic rules handy. So, yeah, anything else before I start? Yeah. Yeah. I want to say no, but no. Yes, you can. Bring the scientific one, so make sure that you can do a logarithmic 10 to the power of x or e to the power of something. And I think one time somebody forgot their calculator, and there's a target like 15 minutes away. Hence the exam. No, you don't need a graphing calculator, but you do need something that you can put a large scientific calculator. Yeah, it's $15 or something like that. Yeah.
For this course, in terms of the exams, so you're saying that this packet is just everything that you're going to review throughout the quarter?
Yep.
Pulled from the book?
Yep.
Pulled from you?
Yeah, well, some of the pictures actually from the book.
Okay.
But yeah.
Okay.
I'm trying to get away from the textbook just because they're pretty simple.
So we should just use the textbook just for maybe further.
Yeah. And if you want to kind of decide, I do recommend the textbook. They're actually a pretty good textbook. It's probably one of the better one.
I just purchased it. I was just wondering in terms of, at the end of the day.
The contents are here.
Okay.
Yeah. Just because the textbook have a lot more than what I want you guys to know, and they go into a lot more details and certain things. So sometimes you don't need it. So yeah. So my question to you is we're just going to focus on the atom first. Majority of the things that we're going to cover is going to be molecular chemistry. Essentially, we're going to be looking at the property of the electrons and how they interact with everything else rather than the nucleus. Because once we get to the nucleus and the property of the nucleus, we get into nuclear chemistry. So if you're going into radiology, which none of you guys are, that's a bit more relevant just because X-rays, gamma rays, and decays and so on and so forth are nuclear properties, and MRIs and things like that. But we're not going to cover that. We're going to primarily focus on protons and electrons. Actually, we're going to focus majority of the time on the electron itself. So my question to you is, what makes up, Jonathan, what makes up an atom? Let me check. How long ago was it? Yeah, neutrons. The nucleus is the things in the middle, and it's made out of a neutron and a proton. So yeah, that's about right. In terms of the charges itself, so you have electrons, which is negatively charged. We have protons, which is positively charged. And do protons and electrons attract one another, or would they repel one another? Protons and electrons, so they would attract to one another. So in quantum mechanics, at least these charged particles, if you have opposite charges, they will attract. And if we have like charges, they will repel. So if you have positive and positive, they will break apart. Whereas if you have positive and negative, they will get closer and closer together. Yeah. So in fact, the negative ends of your battery is where the electron comes out and propagates out. So yeah, once you get to 14B, you're going to learn about electrochemistry, which is the electron literally moves from one atom and physically moves from one side of your battery to the other. The reason why I keep saying that it's, when we're talking about molecular chemistry, we talk about the properties of protons and electrons, because electrostatic interaction, which is what we're calling it for now at least, is probably one of the largest forces there is in the universe. So if you look at the gravitational forces, for example, and the gravitational forces between electrons and protons and compare it to, say, the electrostatic interactions, you get a factor of 10 to the power of 30 times bigger force in electrostatic interaction than it is gravitational force. So that's the reason the chemistry in Mars is pretty much the same as the chemistry on Earth, because, or even if you go to the surface of the sun, the chemistry is about the same, because as long as its electrostatic interaction is about the same, the things that you get is about the same as well. So my question to you is, why is the atom, or I guess the reason why the atom is so small is because the protons and electrons get really, 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 really close to one another, and you get a really tiny atom. So if you look at, compared to the size of the atom versus the size of, say, a lemon, and compare the size of the lemon to the size of the Earth, then you get about the same ratio. So that's how tiny an atom is. They're incredibly tiny. So my question for you, before we go on to all of this thing, is why doesn't the electrons and the protons in the nucleus collapse? So you have, if you have an atom, you have electrons on the outside, and in the inside you have protons as well as neutron. But why doesn't the electrons and the proton collapse together? They have an attractive force, but why doesn't it crunch together? Instead, we have solid objects. Yep. No, nuclear forces, nuclear chemistry, hence we're not going to cover it. Not nuclear forces. That's actually a bit of trick questions. So why doesn't, if you look at the forces in the mathematics, the electrostatic interactions and gravitational force actually have a very similar equation. That is, no, I shouldn't be chewing while I'm talking. If you have a gravitational force, sorry, kind of moving a bit away from here now. If you have gravitational force, then the force is proportional. So you have some kind of constant, which is called gravitational constant, divided by the distance squared. And if you have electrostatic interaction, which is called the Coulombic force, it's also a constant divided by r squared. So they look very similar in terms of one another. And if you can answer why the moon doesn't collapse towards the Earth, then you have the same answer why the electron doesn't collapse towards the nucleus. So why doesn't the moon fall down towards the Earth? Or the Earth towards the sun? What does the orbit do? Why is the orbit stable in the first place?
I mean, isn't it because, well, I mean, in astronomical context, isn't it basically because there's the inertia of the momentum is keeping it in the orbit and there's not enough friction to wear down? But, I mean,
Yes. No, you remember more of your physics than I expect you to. Cool. But it's simpler than that. Yes, there's forces and so on. But as you see here, the forces is just falling down towards the nucleus. Or in the case of the Earth versus the moon, then so that's our moon. So what is the inertia that you're talking about in the first place?
so it would normally just leave the orbit in a different direction if there wasn't gravity.
Well, if there's gravity, then we'll just fall down. But what would... I think you're actually getting to what I'm trying to get to, but I think we're just talking it. We're just talking in slightly different terminologies. So, what is the other thing that the moon is doing other than just standing still? It's moving. It's going around and around and around and around in a circle. So the reason why the moon doesn't fall down towards the Earth is because it's circling about and it's moving really, really fast. Which is why I was saying that the question is actually a trick question, because the fact the moon is falling towards the Earth all the time. So if you have a regular object, right? So if you have the ground, and if I simply toss something towards the ground, we know it's going to fall down. It's going to fall down. But the problem is that because the distance between the moon and the Earth is so far away, we have the Earth here and the moon is right here. The moon is falling down, but as it falls down, or the moon is falling down, but as it falls down, the Earth is curving away from its surface. And then as it falls down again, it curves away, falls down, curves away, and in the end you get this stable orbit that you were talking about before, right? So because the moon is spinning, and in fact it's spinning really, really fast, that's the reason why it doesn't fall down towards the Earth. And that's the same reason why an electron doesn't collapse towards the nucleus either. That's because the electron here is spinning really, really, really quickly, such that even though there is an electrostatic interaction pushing it down towards the nucleus, it curves away from itself. Hence, it never actually collapses. When we're talking about chemical reactions, and if you drive a car, then the energy that is contained from a particular chemical reaction is actually the energy contained in this particular electron. How fast they're moving is literally the amount of energy that we can extract out. there's a limit in terms of how much we can get out of it. But more or less, if you have a chemical reaction, a light is being emitted from the an LED that we have on the light here. It's all about the energy changes that's occurred in the electrons itself. So sometimes, as the molecules in the light bulb there emits some light, the electron is going to move slightly slower, and whatever difference in energy is what we see as light, or as heat, or any particular process that you're interested in. So that's kind of the basic physics that we're going to get to. And again, most of the time we're just going to interest ourselves in just the property of this particular electron. So electrostatic interaction is always there, and it's going to be in the background for whatever it is that we're working on. But that's not all, because the analogy, while pretty similar, fails once in a while. For example, if we have a large enough meteor and crash towards the moon, and if we have a large enough meteor that crashes to the moon, it's going to knock the moon out of its orbit, and then once over time, it's going to fall down towards the Earth. But I can bang on this particular podium, which made it of the atom as well. And essentially what I'm doing here is just banging on this particular electron really, really hard. But no matter what I do, I know that no matter what I do, I know that the electron is not going to collapse towards the nucleus. That's because there's one last thing that we haven't taken into account in terms of this electrons and protons interaction, which is the quantum mechanics. So, so far what we're talking about is we're comparing the moon and the Earth to electrons and protons, and that's what people call classical mechanics. It's just literally an object that's just like a sphere, moving about, circling, and there's some kind of forces around them. But once we get to quantum mechanics, the rules are slightly different, because the reason why the electron, in terms of a quantum mechanical answer why the electron doesn't collapse towards the Earth, is that the electron is not a single unit of particle in space, but rather it is, as long as we don't interact with it, it exists more as a wave that occupies a three-dimensional space. And the best way to think about it is a soap bubble, that the electrons are the surface of the soap bubble that you see in kind of floaters about. And it's a shimmering looking soap bubble. And that's pretty much a pretty good analogy to what an electron is doing. Again, analogy always fails, but if you have a soap bubble and just simply, if you try to put some force on it, it will wobble rather than actually collapsing. That's where the analogy fails, because in fact, soap bubble does burst all the time. But otherwise, sometimes it's better to think about electrons as this wobbly three-dimensional thing around the nucleus itself, rather than an actual object like this. So instead, it exists as a wave. Hence, we're going to go into the quantum mechanics portion, where some of the rule becomes slightly different. But as long as you remember things about, if you can think of these particles like electrons and protons and so on more as a wave rather than an actual particle, then it becomes a little bit easier to remember them. Sorry? This one? Yeah. Well, they're pretty much, there's actually a bunch of stuff here. There's gravitational constant, mass 1, mass 2, and there's some other constants in there, but they're just constant. And what's important about them is just the dependence 1 over r squared. Yeah. I don't remember exactly what they are, but the important part is that part there. The rest is just, you'll see it after you take a lot of science classes, you realize that constant is something that people put in just because the number doesn't exactly fit. And then once in a while, they realize the constant is not actually a constant. It actually changes slightly over time or something. But yeah, but the important part is that experimentally there are square dependence. Oh, actually it's written over here. Anyway, you do not need to know about the details of the equations, but you do need to know more or less how they behave and the general gist of it. What I do want to get to is more or less, for today, is the basic of quantum mechanics, which is the basics of wave and wave properties. And my best analogy and the best way to think about waves is think of it as sound, because that's what we encounter all the time. There's some terminology that you do need to know, which is the simplest wave is called a sinusoidal wave. So it looks more or less like this particular picture. And the important one that I want to mention to you is that a wave have an amplitude. So that's one. It also have the symbol lambda here, which is the wavelength, as well as the frequency. Right. So the amplitude is the height of this oscillation, and usually what you see as intensity. So if you have a really intense sound or a really intense light, what you see is that particular light have a larger amplitude. The wavelength and the frequency is a little bit different. The wavelength is the difference, or I should say the repeating unit. So if I look at from this point here to a repeating unit right here, then the distance is the wavelength. But the thing is that because the wave is fairly uniform and pretty much repetitive, the distance between one place to the other is always equal to the wavelength. So the wavelength is how long before this particular oscillation change sign from positive to negative or top to bottom into its and repeat itself. And the frequency is how fast they're changing. I believe all the definitions are already written out a little bit more exactly on the bottom of the picture, but that's essentially the point. And if you can think about quantum mechanics, at least for now, to think about them closer to the property of sound, then you'll be in much better shape. Where do I want to go from here? Right. So one of them is the amplitude. So again, it's one of the best way to think about these things are think of them as sound. So if you have an amplitude, the higher the amplitude, the louder the sound. Whereas the smaller the amplitude. Oh, shoot. No, yeah. I thought I have my sign in reverse there. But yeah. The larger the amplitude, the louder it is. And then if you have wavelength and frequency, so if you have a wave that looks like this is a long wavelength, where this one is a short wavelength. And same like, very similar to sound, if you have a bass, which is low frequency, then you have a long wavelength and high frequency. Whereas if you have a higher pitch, then you have high frequency, and you have so if you have a higher pitch noise or something that looks like this, you have a higher frequency, as well as a short wavelength. So frequency and wavelength are inversely related to one another. They're more or less telling you a fairly similar information, at least for now. So yeah. So the one that I want you to kind of do remember, just kind of keep in mind, if you have a high frequency, you have a you have a long wavelength. And if you have a high frequency, you also have a high energy. So again, think of it like sound. So if you have a low rumbling, it's low energy, whereas you have high pitch, then it's high energy. That's a good way to think about them.
So the frequency and wavelength are inversely related?
Yep.
So wouldn't they be short?
Oh, yes. What did
Sorry,
I think,
interrupt.
no. I think sometimes my hand and my mouth do not correlate to one another. I usually just write something and then say something else. So yeah, thank you for catching that. But yes, thank you. So high frequency and high energy is that one is correct? Yes. And the last one in terms of properties, some of the waves that I want you to know is the speed. And obviously, since we're talking about sound, then the speed is the speed of sound. But because we're going to talk about quantum mechanics, we're really not interested about the speed of sound, but rather the speed of light. And the speed of light is the fastest speed an object can travel, at least in space. Then the speed of light, we're going to use a symbol of c for the speed of light. And it's a really useful number to remember as well, and it's pretty simple as well. It's 3 times 10 to the power of 8 meter per second is the speed of light. We're going to use it quite a bit, and I don't generally ask you to memorize numbers, but if you remember them, it makes it faster because you don't have to hunt for it. Meters per second, M per S. To the power of 8, yes. Okay. Now, that's more or less where the analogy goes, and in terms of how to think about these quantum mechanical stuff, think about them as wave. If you have high frequency, that means you have a short wavelength because the graph looks like that, like this, shorter. And then if you have high frequency, it's a high pitched noise, it's high energy, something along that line. Let's see. What we're interested in most of the time is actually, for now, we're going to go into the simplest kinds of wave, which is called the photon, or really, it's just a particle of light. In order to understand quantum mechanics, that's photons, or the particle of light, is the simplest kinds of wave there is, and in fact is probably the most common method on detecting chemical reactions and properties of molecules and so on. So here we are. The understanding is about the same. High frequency means shorter wavelength, and high frequency also means higher energy, whereas the inverse is correct. So if you have a low frequency low frequency photon, you have low energy, and they also have a long wavelength. Yeah, so they repeat shorter frequencies. Sorry, could you repeat the question again? Yeah, okay. They repeat. Yeah. Yep. Yeah. They literally oscillate in space longer. So if you have things like radio wave, they oscillate about 1 meter or something like that. So, whereas if we have lights like these, so the redder portion of the light, they oscillate every 700 nanometers, or 700 times 10 to the power of negative 9 meter. So they're fairly short. So which of these wavelengths or type of photons have, I'd like you to, for now, kind of tell me which one is the one with the highest energy and which one is the lowest energy and so on from this list here. And you have some things on the top to help you guide to the question as well. But the particular spectrum is written in terms of frequency as well as wavelength, but it's not in energy. So which of these light is the highest energy? We have gamma ray, visible light, UV, microwave, X-rays, and infrared radiation. So which one is the highest and which is? Yeah, verbally. It's a short one. So gamma rays is going to be highest. Then which one is the lowest energy out of the bunch? Microwaves. Cool. And essentially that's going to be the order we have, and we have some of them on the graphs on the planner as well. So if we order it from the lowest to highest, energy, then we have the lowest energy is microwave. Then the next one we have IR. Then we have visible, we have UV, X-ray, and then lastly the gamma ray, which have a symbol of gamma ray. Can you guys actually read my handwriting? Or not really? No? Yes? Okay. Work in progress as well. Now, okay. It's not that bad. The relationship, so of course this is a science class, so we're also going to look at exactly how they look like in terms of mathematically. I'm not going to ask you about the periods and the frequency, but I do want you to know the equation here for each one and understand the symbol as well. So one of them is the property of the speed. So here we have the speed of a photon, speed of light. So these are how the equations actually relate from one to the other. The speed of light is equals to the lambda here is the wavelength times v, which is the frequency. And when I say the wavelength and the frequency are inversely related, the equation that we're talking about is the rearrangement of the equations on the side there. So if you simply move the lambda down here, we get the second equations, or I should say the first one, that the frequency is equals to c, or the speed of light, divided by the lambda, which is the wavelength. Hence they're inversely related from one another. The next one is the energy, and we mentioned earlier that the energy of the flicker wave is proportional to its frequency. So energy is h here, is another constant, which is called the Planck's constant. H is the Planck's constant, which have a value of 6.626 times 10 negative 34. And V again here is the frequency. Or I should say. Okay. And because we have the previous relationship that the frequency is equals to c over lambda, we can also substitute the relationship, and we get the last, the next equation here is that the energy of a photon is equals to h, the Planck's constant, times c, the speed of light, divided by its wavelength. Let's see, what else do I want to say? We'll get into, there's one other unit conversion that is kind of useful to know, which is called the electron volt. I'm not going to explain what is a volt for now, but essentially an electron volt is a really small number. So it's 1.609 times 10 to the negative 19 joule. And majority of the time, if you're looking at things that are quantum mechanics in nature, most of the time the units are going to be expressed in terms of electron volt because the number is so small. So it's a way for physicists to avoid having to write 10 to the negative 19 all the time. Hence, they write everything in terms of electron volts. We're going to use it later on, but it's just another unit of energy. Just like a meter is a unit of length and feet is also a unit of length, we're going to be using the unit of electron volt quite a lot, rather than joule, for a large percentage of the class, just because they're convenient.
Tests.
Yep.
Are constants going to be provided?
Yeah, constants are going to be provided. You can use it. So yeah, those are going to be provided for you. So I've been talking for about an hour now. So I want you guys to now work on some of these problems. So we're going to be on page 11. Essentially, I want you to convert some of these frequencies into wavelength and energies, and for energy both in joules as well as in electron volts. Why don't we do that for now? So I'm going to close the video, and I'd like you to work on, let's do not the frequency one, but rather this particular one. Yeah. The corner one. So I do want you to finish off this particular table. We're just going to do this as a group. So I want you to, Paul, if you can twist your chair and just kind of work with the rest of the group, because we only have 4 people here. We'll just do that. We'll keep it for about 20 minutes, and then we'll come back into the materials.